Welcome to The Explainer. Today we're taking a seriously cool journey, starting right from the drawing board of power electronic theory and going all the way down to a physical, working hardware build using an Arduino. We're going to decode the pretty complex world of inverters, specifically how we can manipulate digital signals to create perfectly smooth, reliable analog power. If you've ever wondered how massive industrial-scale power systems minimize all that electrical noise, well, you are in exactly the right place. Let's get into it. So, here's our engineering roadmap for today. First, we'll look at the multi-level inverter revolution, followed by a head-to-head comparison of 3-level and 5-level architectures. Then we'll talk about defeating distortion with SPWM strategies, designing LC filters, and finally, our step-by-step hardware build.
But hey, before we touch any hardware, we really need to understand the enemy here. And that enemy is total harmonic distortion, or THD. You can think of THD kind of like static on an old radio dial or a highly pixelated blocky image on your TV screen. It's essentially the unwanted electrical noise or distortion in an AC signal. You see, when we convert direct current from something like a battery into alternating current for our appliances, we want a perfectly smooth, rolling sine wave. THD is that jagged, chaotic static that completely disrupts that smooth wave. And our ultimate goal today is to literally eliminate it.
All right. Section 1, the multi-level inverter revolution.
Okay, so why do we even need to revolutionize things? Well, a standard 2-level inverter is basically just a giant on-off switch. Because it only toggles between positive and negative voltages, it creates a very rough, blocky wave. That leads to high THD and intense switching stresses on your components, making it a pretty terrible choice for high-voltage applications. But enter the multi-level inverter, or MLI. By processing multiple voltage levels, it creates the stair-step effect that naturally mimics a smooth curve. This dramatically lowers the THD, reduces switching stress, and makes it incredibly reliable for high-voltage systems. It's a total game-changer.
Now, for our build, we're specifically focusing on the Cascaded H-Bridge, or CHB architecture. Why this one? Well, compared to other complex structures out there, like diode-clamped or flying capacitor models, the CHB requires significantly fewer components. It completely skips the need for bulky, heavy transformers and those annoying clamping diodes. Plus, because the output of all the modules simply adds together, the voltage rating of each individual module is kept super low. That means the stress on our individual devices is greatly reduced, which makes our entire system far more robust.
Moving right along to Section 2, comparing 3-level and 5-level architectures.
This comparison perfectly illustrates our core concept. A 3-level inverter produces 3 distinct voltage steps: positive, 0, and negative. Sure, it's better than a standard inverter, but the output waveform is still quite rough, which leaves us with higher harmonic distortion. But when we upgrade to a 5-level inverter, we introduce 2 intermediate voltage steps. Imagine you're climbing a staircase. A 3-level staircase has these massive, giant steps that are a real workout to climb. A 5-level staircase? Smaller, much more manageable steps. In electrical terms, adding those 2 extra levels transforms our jagged output into a visually smoother wave, which drastically reduces our harmonic distortion.
Let's put some hard numbers to this with our simulation data, because the contrast is stark. When we run a simulation with a carrier frequency of 19 times 50 Hz, the 3-level inverter suffers from a massive THD of 51.91%. But at that exact same frequency, the 5-level inverter cuts that distortion nearly in half, plummeting all the way down to 26.61%. And that trend holds absolutely steady across different frequencies. Simply adding those extra 2 voltage levels yields a massive, undeniable improvement in the purity of our power.
Which brings us to Section 3, defeating THD with SPWM strategies.
So how do we actually control these extra levels? We need to introduce SWPW, or a Sinusoidal Pulse Width Modulation. You can think of SWPW as the highly intelligent brains behind our inverter switching mechanism. It constantly compares a high-frequency triangular carrier wave against our ideal reference sine wave. Based on exactly where those waves intersect, it calculates the precise microsecond to switch our transistors on or off. It's essentially a brilliant way of digitally faking a perfectly smooth analog signal.
Through our simulations, we can track exactly how the modulation index, which is just the ratio of our reference voltage to our carrier voltage, actually affects our output. When we push that modulation index perfectly to 1 in our 5-level simulation, we hit a benchmark total harmonic distortion of exactly 27.11%. And as the modulation index increases, our THD factor reliably decreases. But it's important to note the actual strategy we use to arrange those carrier waves matters immensely.
The data here reveals a real goldmine of insights. We're constantly balancing two variables: total loss, which includes your switching and conduction losses, and our main enemy, THD. Now, phase disposition gives us a really solid THD of 26.87% with fairly low losses. But consider carrier overlapping C. By inverting the phase of neighboring carrier waves, we achieve the lowest possible THD in our tests, down to 24.95%. The trade-off? Our total switching losses rise slightly to 0.03908. As engineers, we always have to make a choice. Do we prioritize absolute power efficiency or absolute signal purity?
Okay, Section 4, Designing the LC Filter.
So we've used a 5-level architecture and some really advanced SPWM to get our distortion down to around 25%. That's great, but we still have a stepped, rippled waveform. So how do we mathematically force those remaining voltage ripples into a perfectly clean, continuous sine wave before it actually reaches our appliances? Simple. We use an inductor-capacitor, or LC, filter.
To design this filter properly, we first have to establish our strict base parameters. We're feeding the system an input voltage of 100 volts. We demand an output power of 1000 watts, which, with our specific load, gives us an output current of 10 amps. Most crucially, we are setting our ripple current tolerance at exactly 20% of the rated current. That 20% tolerance is the hard mathematical boundary we are designing our physical components around.
When we run all those parameters through our equations and factor in our switching frequencies, we get our exact hardware requirements. To clean up our specific 5-level simulated wave, we need an inductor rated at 8.83 millihenries to resist the changes in current, and that gets paired with a capacitor rated at 0.286 millifarads to absorb any voltage spikes. This exact pairing creates the physical bottleneck that literally forces our stair-step wave into a beautifully smooth curve.
Finally, the really fun part. Section 5, Hardware Build with Arduino and MOSFETs. Let's take all this theory and build it out in the real world, step by step. First, we finalize our optimized SPWM signals perfectly in our MATLAB and Simulink software. Second, we flash that precise SPWM logic directly onto the microcontroller of an Arduino Uno. Third, we physically wire up 4 765p MOSFETs into our H-Bridge configuration right on the breadboard, making sure to connect their gates to the Arduino. Finally, we power up the DC supply and hook up an oscilloscope to measure our real physical AC output.
The trusty Arduino Uno is absolutely the heart of our physical build here. Out of its 13 available signal pins, we specifically utilize 6 dedicated pins. That's pins 3, 5, 6, 9, 10, and 11 to output our modulation signals. Now, before trusting the complex SPWM, we first validate the circuit by sending a basic rectangular pulse to the MOSFET gates. Because let's be real, nobody wants to smell burning silicon. Once we confirm the H-bridge is firing correctly without short-circuiting, we deploy the complex, simulated SPWM pulses. The Arduino is now acting as an incredibly fast, precise conductor, dictating exactly when each individual MOSFET opens and closes.
So why do we go through all this trouble? Why the 5 levels, the complex SPWM code, and the precisely calculated LC filters? Because, as the engineering principle states, lower THD in power systems means higher power factor. The power factor is just the ratio of the actual true power doing work in your system to the apparent power flowing through the circuit. By crushing our harmonic distortion, we drastically improve that power factor. We make the entire system massively more efficient, significantly safer for sensitive electronics, and just far less wasteful overall.
We've seen today how stepping up from a 3-level to a 5-level Cascaded H-Bridge inverter cuts distortion in half, and exactly how Arduino-driven SPWM smooths it out even further. But I want to leave you with this provocative thought. If 5 levels are this much better than 3, what about 7 levels or 9? At what exact point does the sheer physical complexity of adding more MOSFETs, more isolated DC sources, and increasingly intricate code ultimately outweigh the mathematical gains in power efficiency? It's the ultimate engineering balancing act. Thank you so much for joining me on this explainer, and keep questioning the limits of the hardware around you.